Welcome back to Talk Tensors, where we always love to kind of dig into some really cool ML research. And today, I think we've got a particularly interesting one from the title alone. It's called Explaining Control Policies Through Predicate Decision Diagrams. So, anyone working in AI these days, especially with these complex systems we're building, like, think self-driving cars or robots that are getting more and more sophisticated. Well, the controllers, the parts that are making the decisions, those are becoming crazy complicated, right? I mean, it's just not realistic to think we can hand design those anymore.
Yeah.
So we're relying there and more on these automated techniques. And that's awesome because, they can churn out some seriously effective controllers. But there's a catch, right?
Right.
These automated systems are often like total black boxes.
Yeah.
We don't really know why they make the choices they do. And that lack of transparency is, I think, a pretty big deal, especially when we're talking safety critical stuff. Things where a wrong decision could have serious consequences.
I think that's the key point, right? If we as engineers, the people who are, supposed to be building and understanding these things, if we can't even grasp how the controller is actually working, its underlying logic, then how on earth can we be sure it's going to be reliable? Or how can we adapt it to new situations? And probably the biggest one, how can we actually vouch for its safety? Especially when it comes to, getting these things approved by regulatory bodies, there's just this huge push. And in some areas, it's even becoming a legal requirement for AI systems to be explainable.
Yeah.
So this isn't, some kind of a purely academic exercise, right? This is something that has very real world implications.
Totally. And so that's where, explainable AI comes into the picture. And when we talk about making AI understandable, decision trees, or DTs, as I'll probably just call them, they've been a go-to tool for a long time, right? I mean, they're pretty easy to follow, even for non-experts, I'd say. And they allow us to incorporate like our real-world knowledge, domain expertise into the system by using these kind of if-then rules. Conditions like if the rain sensor is on or if this object is classified as a pedestrian. The paper actually has a nice figure 1, I think it is, that shows how DTs can represent different kinds of control strategies. Mm-hmm. Some that are very straightforward, like if this, then that, and others that are a little more flexible where multiple actions might be allowed.
Yeah, and it's actually amazing how widespread DTs have become specifically for representing controllers.
Yeah.
I mean, you just look at the number of citations in this paper, like they mention 5, 7, 8, and there are, tons more. And these are all coming from like very different areas of research in both ML and control theory. You've got probabilistic systems, reactive synthesis, even hybrid systems, which kind of combine continuous and discrete dynamics. And there's even this specific tool they mention called DT control. I think it's references 6, 7, which is designed to automate the creation of these DT-based controllers.
Oh, cool.
So it's not just, a theoretical concept. People are really using these things in practice.
Totally. All right, well, let's shift gear for a minute and talk about another kind of diagram that's been really successful, especially in hardware verification and circuit design, and that's binary decision diagrams, BDDs. Now, their real strength is their ability to represent tons of, Boolean information in a really compact way. Mm-hmm. And they do this by, kind of taking advantage of these bit-level representations and some pretty clever reduction techniques.
It's actually fascinating how BDDs achieve that compactness.
Yeah.
They essentially break down these complex logical statements into their fundamental building blocks, these binary components, and then they use these very sophisticated merging algorithms. They can identify and merge, sections of the diagram that are structurally the same, even if they represent different parts of the overall logic. And this lets them handle really, really complex Boolean functions very efficiently. And they've even been used in representing, some aspects of controllers, things like planning strategies for AI agents or for controlling hybrid systems, as they mention in some of the citations. They give examples like 21, 26, and 40.
Okay, so that's pretty cool. They're good at being compact, but even though they're so efficient, BDDs haven't really taken off as the standard way to actually explain how a control policy works, to make it understandable to a human. And the paper digs into a few key reasons why, I think. So first off, DTs, they use these more natural, human-readable predicates, these conditions that we can easily understand. Whereas BDDs, they're operating at the level of raw bits, zeros and ones. It's much easier for us to wrap our heads around something like engine temperature greater than 90 degrees than it is to decipher a string of like 01 and 101, whatever.
Exactly.
Second, DTs give us more flexibility in the order of those conditions.
Yeah.
Which can actually lead to, smaller and more intuitive structures. And then finally, the way DTs are learned, they can cleverly deal with these don't care scenarios to kind of minimize the size of the tree. And that's not quite as straightforward with regular BDDs.
You hit the nail on the head there, that fundamental difference in how they represent information, right? So DTs with these high-level predicates that we can understand versus BDDs with their low-level bit victors, that's a huge deal when it comes to interpretability.
Yeah.
BDDs are fantastic at representing logic in a compact way, but that representation, it can often obscure the higher level reasoning, which is much more transparent when you look at a decision tree.
Okay, so now I think we finally get to the real heart of this paper. And that's where they introduce a new approach called Predicate Decision Diagrams, so PDDs as they call them. Think of PDDs as kind of this attempt to get the best of both worlds.
Okay.
They keep those interpretable predicates that make decision trees so understandable, but they also bring in those reduction techniques that make BDDs so darn compact.
Right.
So it's really about bridging this gap between being able to explain how something works and being able to represent it efficiently, which, that's a pretty fundamental problem in a lot of AI research, isn't it?
It really is, and it's quite fascinating to see how PDDs sort of build upon this whole history of decision diagrams, right? Like, they point to all these related research efforts, like you have edge-valued BDDs, where they use integers on the edges to encode more complex transitions.
Oh, interesting.
And then there's this idea of combining BDDs with SMT solvers, which are these powerful tools for reasoning about logical formulas. And that lets BDDs handle, predicates that are more than just simple Boolean variables.
Okay.
But they really emphasize these things called linear decision diagrams, or LDDs, as sort of the most direct predecessor to PDDs.
Okay.
Because LDDs can actually handle these linear arithmetic predicates. But like we touched on earlier, there's this recurring challenge with all of these more expressive decision diagrams.
Yeah.
And that is that you can end up with inconsistent paths, like scenarios where the combination of predicates along a particular path actually leads to a logical contradiction. And they even cite a bunch of papers where this has been an issue, like 19, 30, 31, 49, and 58.
Interesting. Well, and there's been other work too, right, on trying to make decision diagrams more explainable.
Oh, absolutely.
Like, I think they mentioned template decision diagrams.
Yeah, TDDs.
Which I guess are trying to capture common decision-making patterns to make things, more structured and understandable.
Yeah.
And then there's also all this recent work on actually learning decision diagrams directly for classification tasks. So clearly people are really interested in tapping into that inherent interpretability that decision diagrams can offer.
Yeah, for sure.
Okay. But back to PDDs, I'm kind of curious, what's the formal definition? Like, how do they actually work?
Yeah, so they do give a formal definition, but I think the key takeaway is that unlike traditional BDDs where the decision nodes are based on, just these simple Boolean variables, in PDDs, those nodes are actually labeled with richer predicates.
Okay.
So the kinds of conditions that we've been talking them, things that might involve comparing, variables to values or more complex relationships.
Yeah.
And the other cool thing is that the terminal nodes in a PDD, instead of just specifying a single action, they can actually represent sets of allowed actions.
Oh, okay.
So this lets you represent these more flexible control policies where there might be multiple valid choices in a given state.
So it's not just like, if this, then do this specific thing.
Exactly.
Like, if this, then you have some options.
Exactly, yeah.
Okay. Well, that's pretty neat. But how do they actually fit in with DTs and BDDs? Like, what's the relationship?
Yeah. So the paper explains that a standard decision tree, you can actually think of it as a special kind of PDD.
Okay.
Where the underlying structure is just a tree. There's no sharing of nodes or merging of subdiagrams. And then on the other hand, a traditional BDD, that's like a reduced ordered PDD. But the catch is that all the predicates it uses have to be simple Boolean predicates, just operating on single bits.
Gotcha. Got it. So it's like PDDs kind of generalize both of those concepts.
Exactly.
But how do they actually create these PDDs? Like, where do they start?
Right. So the really clever part is they start with an existing decision tree.
Okay.
So you've got your decision tree, and they have this whole process for synthesizing a PDD from that. And it involves a few key steps. So first, they go through the decision tree, and they find all the unique predicates that are used in it.
Mm-hmm.
And then they treat those predicates as the fundamental variables when they're building this new BDD-like structure. And they call this predicate bijection. It's basically a mapping from the predicates to the variables of the new diagram.
So they're taking those meaningful high-level conditions from the decision tree and then using those as the building blocks for something that's more compact.
Yeah.
Okay, I like that. It's very intuitive.
Exactly. And this lets them use all those, powerful reduction techniques from the BDD world.
Oh, okay.
Like they can identify and merge isomorphic subdiagrams, which are parts of the diagram that are structurally the same, even if they, represent different parts of the logic.
Gotcha.
And by merging those, they can shrink the PDD down quite a bit. They also use these variable reordering heuristics, which are essentially algorithms for finding a better order for those predicate variables.
Okay.
Because the order you put them in can actually have a big impact on the final size of the PDD. One of the well-known algorithms they mentioned is Rudel's sifting algorithm, which I think is reference 55.
Okay.
And that's a pretty common technique for optimizing BDDs.
So it's not just about inheriting the predicates from the decision tree. They're also using all these optimization tricks from the BDD world to make the PDD as small as possible.
Exactly. And the optimization doesn't stop there. They also do this thing called care set reduction,
Okay.
which is based on work by Cooter and Mondre, I think reference 22. And the idea here is that, a controller's policy might not need to be defined for every single possible state of the system.
Right.
So they can actually focus on just the care set of states, the states that the system can actually reach or where the controller's decisions actually matter.
Okay.
And this lets them compress the PDD even further by merging nodes that have the same behavior within that relevant part of the state space.
Makes sense. Why bother with parts of the state space that the system is never going to see?
Right.
Just get rid of those irrelevant branches, make it more efficient.
Yeah, absolutely. But there's this tricky thing that happens when you start treating these potentially complex predicate as if they're independent variables in a BDD-like structure.
Okay.
And that's that you might end up with logically contradictory paths.
Uh-oh.
So, for example, you could have a path in the PDD where one decision is based on, let's say, temperature is less than or equal to 19 degrees.
Okay.
And then further down that same path, you have another decision that's based on, let's say, temperature is greater than 20 degrees.
Well, those can't both be true.
Exactly. You can't have both of those things be true at the same time. So the authors, they came up with a specific mechanism to detect these kinds of inconsistent branches and then get rid of them.
Okay.
To make sure that the final PDD actually represents a, coherent and valid control policy.
That makes a lot of sense. So they're not just blindly applying BDD techniques. They're also thinking about the meaning of those predicates and how they might depend on each other to make sure everything stays logically sound.
Exactly.
And I guess that's super important if you want the PDD to be, not just compact, but actually interpretable.
Yeah, that consistency check is really crucial for the whole explainability part. I mean, if you're trying to provide an explanation that has logical contradictions in it, then it's not really much of an explanation, is it?
Right. It defeats the whole purpose, right? So they've got their PDDs, they've got a way to construct them, but how do they know if it actually works? Like they got to test it out, right?
Right.
And that's where the experimental evaluation comes in. They've got those research questions that we talked about earlier. So let's start with RQ1. How do the sizes of PDDs compare to those traditional bit-blasted BDDs?
Yeah, so this is, I think, one of the most fundamental questions because, like we said, the common way to represent controllers with BDDs is to do this bit blasting thing where you encode every state variable as a bunch of individual bits.
Yeah.
And the authors, they figured that PDDs, by working directly with these higher level predicates, they could avoid that, that often huge blow up in size.
Okay.
And the results that they present in Table 1 and Figure 5 are, I think, pretty impressive.
Yeah.
They found that across their benchmarks, the PDDs were much smaller than the bit-blasted BDDs. I think the average size reduction was something like 77%.
Wow. That's a lot.
Yeah, it's really significant. And they even highlight a few specific examples that I thought were particularly interesting. So for benchmarks like Bloxworld.5 and CDrive.10, the bit-blasted BDD representations were actually bigger than just using a plain old policy table.
Oh, wow.
Which is, I mean, that's kind of the most naive way you could represent a policy, just listing out all the state action pairs. But the PDDs were still much more compact in those cases. So their conclusion is that by avoiding that bit-level encoding and by working with predicates directly, PDDs can be a far more concise way to represent control policies.
Okay. That's a big win for PDDs.
Yeah.
So then what about RQ2? Can they represent controllers more concisely using PDDs than with, the original decision trees they started with?
Yeah, that's a really interesting question because there's this trade-off, right?
Right.
Decision trees, they have this flexibility in how they order the predicates.
Right.
This can be a real advantage in terms of keeping the tree small because you can put the most informative conditions higher up in different branches, and that can sometimes lead to earlier termination.
Gotcha.
But when you introduce a fixed ordering with PDDs, that might make the initial structure bigger, but the benefit is that you can now merge those identical subdiagrams, and that can lead to some pretty dramatic reductions in size, especially when you're dealing with more complex policies where, the same logical conditions might be checked in different parts of the decision-making process.
Okay, I'm following. So what did they find?
Well, in Table 1 and Figure 6, they show that, on average, the PDDs were about 16% smaller than the decision trees.
Okay, that's not bad.
Yeah, it's a decent improvement. It really shows how that merging capability can pay off. And they also highlight a specific case, the 10 rooms benchmark, where the PDDs were significantly smaller than the decision tree. And then they point to this column in Table 1 called #shared. And Figure 7 kind of illustrates this trend where as the systems get larger and more complex, like they have an example with the Israeli Jalfan protocol, the percentage of shared nodes in the PDDs increases.
Interesting.
So that means that the node sharing is becoming even more effective as the complexity of the control policy grows.
So they're not just smaller than bit-blasted BDDs, they're also, in many cases, smaller than the original decision trees.
Right, exactly.
Pretty cool. All right, so last research question. RQ3, what's the impact of those different optimization steps they use? The consistency enforcement, variable reordering, and care set reduction. Like, how do those affect the final size of the PDD?
Yeah, so in Table 2, they give us a nice breakdown of how each of those steps contributes to the overall optimization. And one thing that's interesting is that when they first impose a fixed order on the predicates, which they have to do to allow merging, that can sometimes actually make the diagram a bit bigger compared to the original unordered decision tree.
Oh, really? So it's not always an immediate win?
Yeah, because by forcing a specific order, you might lose some of the efficiency that the decision tree had from being able to order its checks differently in different branches.
Okay, I see.
But then the next step, variable reordering, that often has a really big impact, especially for the larger, more complex benchmarks, like I think Newly Zuck.5 was one of them.
Mm-hmm.
They found that using good reordering heuristics could cut the number of nodes in half in some cases.
So finding the right order for those predicates is really key.
Oh, absolutely. And then after reordering, you've got the consistency transformation where they get rid of those logically inconsistent branches. And that also helps to reduce the size further, like in that Newly Zuck.5 example, enforcing consistency shrunk the PDD by a whopping 85%.
Wow.
And then finally, care set reduction. That takes advantage of the fact that the control policy might only be needed for certain parts of the state space.
Right.
And they saw reductions of up to 68% in some cases, like with CDrive.10, I think was one example.
So it's really a combination of all these techniques working together that makes the PDDs so compact.
Yeah, exactly. It's this, multi-stage optimization process. They start with the decision tree, represent it as a BDD, and then they refine it step by step to make it smaller and more logically sound.
Okay, so now for the fun part. What are some of the future directions that they talk about? Like, where could this research go next?
Well, one of the most exciting ideas they propose is to try and make the decision tree learning process more aware of the fact that it's going to be used to create a PDD.
Ah, okay. So instead of just learning a good decision tree in isolation, you try to learn one that's specifically designed to play nicely with the PDD construction process.
Exactly. So the idea is that if you can bias the way the decision tree selects its predicates, if you can encourage it to choose predicates that are more likely to lead to shared subgraphs in the PDD, then you could potentially end up with even more compact and explainable representations.
Yeah, yeah. Make the initial learning step sort of anticipate what's coming next. I like that.
And they also give a little bit of detail about their experimental setup. They mention the hardware they use and the software tools, like the DT control tool for working with decision trees and the BDD library for BDD operations. And they also point the reader to Appendix B, where they have this whole case study using the triangle tire world example.
Okay.
And they actually show the PDD that they got for this problem in Figure 9. And it's a really nice illustration of how the PDD can give you a much more concise and understandable representation of the optimal control policy, like way better than a traditional policy table or a bit-blasted BDD. And they highlight how you can actually see some of the key decision-making logic in the PDD structure, like when and where to pick up a spare tire along the optimal route, which they show in Figure 8b.
Oh, cool. So you can actually see like the reasoning process in the diagram.
Yeah, exactly. And it's a much more compact representation than you would get with those other methods. I think the bit-blasted BDD for that example had something like almost 3 times as many nodes.
Wow. Okay. So it's really a practical demonstration of how PDDs can balance, being understandable with being efficient.
Yeah, absolutely.
So just to wrap things up, the big takeaway here is that predicate decision diagrams, they're this new way to represent control policies, and they seem to have a lot of potential. They take what's good about decision trees, the explainability, and they combine it with the efficiency of BDDs. And the research shows that they can be just as compact as decision trees, and they're way more compact than those traditional bit-blasted BDDs.
And I think this is a really important step towards being able to build AI systems that are both effective and understandable.
Right. Especially as we move towards, more and more autonomous systems, being able to understand not just what the AI is doing, but why it's doing it is going to be crucial.
For sure.
And, makes it wonder what kinds of new applications or maybe even new certification standards might become possible if we can, represent these control policies in a way that's both efficient and explainable.
Yeah, that's a really good point.
It's definitely something worth thinking about as you continue your own work in ML or AI or really any field where these kinds of systems are becoming more and more prevalent.
I agree.
Well, thanks for joining us for this deep dive. We'll see you next time on Talk Tensors.